Hello, I'm going to give a brief introduction to word embeddings. Word embeddings build on the work of more traditional NLP systems like latent semantic analysis, and they provide a better foundation for a wide range of machine learning applications. In particular, they allow a machine learning system to be trained efficiently as the number of words in your vocabulary grows without requiring massive amounts of annotated data. They also provide a path to share information between similar words, synonymy, or handle words with multiple meanings. All word embeddings are based on the same insight, that you can derive a lot of information about a word simply from how it's used. By looking at the context of a word, you can predict many properties of it. For example, here are 3 sentences taken from Harper Lee's To Kill a Mockingbird. In each case, I've blanked out a word. Can we guess what those words are from context? We leapt over the low blank that separated Miss Rachel's yard from our driveway. The correct word is wall, but it could equally well have been fence, hedge, or possibly even ditch. Atticus's office was in the blank when he began his law practice. The correct word is courthouse, but it could have been any building. Your daughter gave me my blank lesson this afternoon. In this example, it could have been piano or dancing, but the correct answer is first, which does fit well. The principle of knowing words by the company they keep is also known as the distributional hypothesis, which strictly is that similar context implies similar meanings. So what is a word embedding, and how does it represent the semantics of words? A word embedding represents each word as a vector of real numbers. 2 words are compared by comparing those vectors. Words are supposed to be similar in the embedding to the extent that they collocate in the corpus of documents we trained on, specifically if one word appears in the context of the other. By the way, I don't intend to address the philosophical question of whether this is really representing the semantics of words or merely behaving as if it is. Every word in your vocabulary is represented by a list or vector of numbers. If you've ever looked at a bag of words, you may have encountered the one-hot encoding, whereby you have a vector that is the same length as the number of words in your vocabulary, where you put in a 1 to represent the word that you've encountered, and zeros everywhere else. This is not how word embeddings work. Instead of having a column for every word in your vocabulary, you set of a fixed number, typically 300. So instead of being full of 1s and 0s, they can take any real number. So a word like cat will be represented by a list of 300 real numbers, which we can also think of as a point in some 3-dimensional space. When people first encounter word embeddings, a common question is, what do the dimensions mean? The diagram here at the bottom right suggests that you could distinguish various types of animal by the extent to which they're domesticated, whether they're commonly kept as household pets, or whether they're fluffy. But you shouldn't take that too seriously. While it is sometimes possible to interpret the dimensions of an embedding, you should just treat them as numbers that have useful properties and not think too hard about what each dimension means. When you have an embedding, how do you compare 2 words to see how similar they are? You do that by comparing the 2 vectors. There's a number of ways to do this, but the most common is called cosine similarity. This says that you stand at the origin and you see whether the 2 points are in the same direction. If they're in the same direction, they're similar. If they're in opposite directions, they're dissimilar. And if there's somewhere in between, then there's somewhere in between. Similarity is scored from -1, meaning dissimilar, up to +1, meaning highly similar. And how do we know whether we should treat 2 words as similar? That all comes back to collocation in the corpus of training documents. So our corpus here is a large supply of English documents, say thousands of books, but they're completely unannotated. No one has marked them up for us or taught us anything about the vocabulary. All we can tell is which words appear near to which others. Another way to look at this is in terms of substitutability. Two words will be similar if we can often substitute one for the other, such as wall and fence, even though their meanings differ slightly. So we're going to be looking more closely at three major word embedding algorithms. Word2Vec was the first to come out and represented a major shift in approach for machine learning on natural language. GloVe came soon after and had some interesting improvements, and FastText is a fairly recent addition that has some really interesting tweaks that we'll talk about. First, looking at Word2Vec, and much of what I say here is going to apply to all of them. The first thing you do is you initialize all of your vectors randomly. Then you go through your training corpus, and for each word, you consider its context. So here we're looking at the word mat, and its context is the 5 words before. The cat sat on the. So this is what we call a positive example. So what we're going to do is tweak the values of the vectors so that the context words move closer to the focal word, mat. At the same time, we're going to pick 10 random words to use as negative examples. Now, it's possible that we might end up picking a word that is similar to the focal word or which is substitutable, but on average, they will tend to be dissimilar and inappropriate. And what we're going to do is we're going to tweak the values in our vectors to move the context words and the negative examples further away from each other. And this is actually a very good example of how machine learning works in almost any context. You run through all your training examples, and for each one, you adjust your parameters slightly so that the positive cases get better scores and the negative cases get worse scores. So by this point, you might be wondering why we're bothering with all this. If we want to know whether two words tend to collocate in the corpus, we can measure that directly. If we want to know if two words appear in similar contexts, we can do that as well. So what does a word embedding do for us? For one thing, it's a much more compact representation than either looking at the entire corpus or storing the collocation matrix. If you have 1 million words in your vocabulary, then you have 1 trillion possible collocations to store. A typical word embedding would only store 300 million numbers, which is much smaller. For another, it turns out that these representations for words that we've just learned can be used for other tasks that are not obviously related to collocation. So this machine learning technique, whereby we do most of our training on one task that we have a lot of data for, and then use the results in another task where we may not have enough training data, is known as transfer learning. Word embeddings are a form of transfer learning. They can be used out of the box for some tasks and can be retrained for others using very little training data. One interesting emergent property of word embeddings is that when a pair of words stand in some particular relationship, that will tend to be reflected in a consistent relative position in the vector space. For example, here are pairs of words that differ in gender: man, woman, king, queen, and so on. They've been projected down into 2 dimensions here so that we can visualize it. Notice that in all of these pairs, the 2 words are roughly the same distance apart, and the female word is always roughly straight up from its male counterpart. The last example demonstrated gender shift. Here we see triples of the different inflections of adjectives. So the shift from positive to comparative has a characteristic direction and length, as does the shift from comparative to superlative. There are many other examples, not only of inflectional and derivational morphology, but of semantic relationships like capital city, CEO, and so on, which we'll see in some later examples. One task that people commonly use as a test for word embeddings is the analogy task. Here you provide words from the first 3 columns and ask for the 4th column. For example, Athens is to Greece as Oslo is to what. To use the word embeddings for this task, we reuse the translation vector idea from the previous diagram, and we treat it as a parallelogram. So we can say king minus man plus woman equals queen. Here's a similar task. We define a relationship from a single pair, for example, France and Paris, and then find other pairs that stand in the same relationship, for example, Italy and Rome. These examples are all taken from the seminal Word2Vec paper. Moving on from Word2Vec and thinking about glove, the vectors are trained in a slightly different way. What they do is they consider pairs of words, for example, ice and steam. Now, in some sense, these represent the same underlying concept, and they differ in just one aspect, but it's quite an important aspect. So when we look at the collocations of other words with ice and steam, we don't just look at whether they collocate strongly or weakly, but we look at whether they collocate with one more than the other. We look at the ratio between the collocation rates. For example, solid and cold appear much more often with ice than with steam. And in contrast, gas and hot appear much more often with steam than with ice. The word water is strongly related to both ice and steam, but it doesn't collocate much more with one than with the other. So we can't use it to distinguish between them. The word fashion is not strongly related to either, and therefore rarely appears with either. So when you're training glove, you look at the words that are good discriminators and you ignore the words that are poor discriminators. Fast text has three major innovations over Word2Vec and glove. They deal with phrases, position, and subword features. So fast text is able to deal with phrases. So the way they do this is they select some bigrams or two-word phrases from the training corpus using a metric called mutual information. This essentially measures whether two words appear together more than would be predicted by random chance. For example, the phrase New York appears far more often than might be predicted from the prevalence of the words new and York. Having identified interesting bigrams, the pair of tokens is replaced with a special token representing the phrase, but they only do this half of the time. The reason for this is that even strong bigrams can also appear together by chance. For example, in the phrase, the new York to Leeds motorway, the words New York do not denote an American city. This process is repeated several times, allowing it to build up longer phrases. Interestingly, they claim that this improves the performance of the embeddings even if the final application doesn't use phrase embeddings, but relies solely on the word embeddings. Approaches like Word2Vec and glove treat all context words equally regardless of order. This bag of words approach to natural language processing emits valuable information and hence cannot reflect the nuances of syntax. Fast text solves this by additionally learning a vector for each position in the context, representing one word before, two words before, and so on. So if the context is 10 words long, it would learn an additional 10 vectors. And when we compare the context to a focal word, instead of just averaging the vectors for all the context words, we first multiply each of them pointwise by the vector associated with the position it occupies in the context. Hence, some dimensions of the embedding space may have more effect in one context position than in others. In addition to learning embeddings for whole words, fast text also learns embeddings for every 3 to 6 character engram. The final embedding for the word is therefore the whole word embedding plus the mean of the character engram embeddings. Because of these subword features, fast text is learning how to compose the meaning of a word from its component parts. When we encounter an unfamiliar word, we not only look at the context, but also try to break the word down into parts. We may be familiar with the etymological roots of the stem, or we may be able to identify prefixes and suffixes and draw conclusions about the derivational and inflectional morphology. By using the character sequences within the word, fast text is doing something similar, albeit less informed about structure. With this interpretation, the residual whole word embedding is arguably the difference between the etymological meaning and the actual meaning. I think of this as being similar to distinguishing between the compositional and non-compositional semantics of a semi-compositional phrase. Another interesting thing about fast text that comes as a consequence of subword features is that it can handle out-of-vocabulary words. If it has no whole word embedding for a word, then it can simply use the embeddings from the sequences of characters within the word. This is important because it means fast text can get away with a much smaller vocabulary and hence a smaller model size. So how do word embeddings handle polysemy and synonymy? When a word has multiple meanings, the embedding of that word will tend to be the average of the embeddings of its various meanings. So the word bank might end up halfway between river and money. Synonyms tend to be highly substitutable, so they will tend to have similar embeddings because you can swap in one for another. I've included a few links of online demos so that you can play around with using word embeddings for yourself. I'll go through some short examples. For the first one, I remember to use the English corpus, and then I see what is similar to the word Obama. And it tells me Obama is similar to Dems, Americans, Washington, America, Libs, POTUS. That sounds about right. Moving on to the analogy task, I can type man is to woman as king is to queen or monarch. That sounds right too. I can use this tool to demonstrate that word embeddings are not magically learning an idealized view of the world, but they're merely reflecting the biases that can be extracted from the training corpus. If I change this example slightly and I ask, man is to woman as doctor is to, then you'll see I get nurse in the top two results. This is because of gender coding in the corpus that we trained on. Our algorithm has learned something we didn't want it to. And there's a whole research area in how to debias machine learning. In this second demo, we can see a three-dimensional visualization of a 200-dimensional embedding. So here I can type a word like Brooklyn, and I can see that Dodgers, Bronx, Yankees, Queens are all close to Brooklyn. But not only that, but I can look at this diagram in the middle and see their relative position. See that some things are grouped on one side and some things are grouped on the other. In this third demo, we can actually see word-to-vec learning happening before our eyes, albeit on a small scale. So I'm going to select the king-queen corpus and then train for 1,000 epochs by clicking on the 500 twice. Note that if you look in this text box here at the top left, you can see the training corpus we're using. It's just a short list of pairs of contexts and targets. When the training is complete, I'm going to select the PCA visualization, and here you see the terms laid out at the bottom right. If you look closely at this, you can see the same analogy example we've been using, man is to woman as king is to queen, laid out as a parallelogram in the embedding we've just learnt. So There are many applications for word embeddings, such as machine translation, generating captions for images, generating summaries for documents, document classification, fact extraction, sentiment analysis, and more. Many of these use a sequence of word embeddings as either input or output. Handling a sequence of arbitrary length takes us into a more complex area of machine learning called recurrent neural networks, which is beyond the scope of this talk. So in summary, a word embedding learns how to represent each word with a vector of numbers. The training process uses the collocation of words in some corpus of documents, such as thousands of books. Words that tend to be substitutable will tend to be similar in the vector space. For pairs of words that hold some relationship to each other, like capital city or male female or noun verb versions of each other, they will tend to have a consistent vector translation between them. Thank you.